Okay, this is the last section of the fourth session of our Introduction to Multivariable Calculus. So in this very last section, we're going to talk briefly about triple integrals. They're not actually super interesting to think about just because they work the same as double integrals, so it's kind of a little bit repetitive to spend too much time on these things, but we'll just start by going over the basics and then doing a couple examples. Now, in single variable calculus, we have a dx at the end of the integral because it's just a tiny unit of length. For double integrals, we'll have some tiny unit of area. And now with triple integrals, we're going to notate this last little piece with a dv because it's a tiny unit of volume. These things aren't really super easy to visualize because they measure something one dimension up from volume, so we won't really picture it anymore, but this little tiny element here does represent a tiny unit of volume, and then we're multiplying that by a function. So all the friendly properties are the same. Things are really particularly easy as long as you're on this nice, I don't know, like it's not a rectangle, but like a rectangular prism sort of region or solid. So this is a triple integral over this solid box. X goes from -1 to 2, y goes from 0 to 3, and z goes from 0 to 2. And we're actually, doesn't really matter, but I'm going to do it in exactly that order. So x is going to go from -1 to +2. This is going to be dx on the outside. Then y is going to go from 0 to 3. Our second integral will be with respect to y. And z goes from 0 to 2. So dz is our last piece. And then the integrand is 12x y squared z cubed. So first piece is first. I'm going to do this little inside integral with respect to z before I do anything else, which becomes just that inside integral becomes 12x y squared, all of these things are constant, times z to the 4th over 4, which simplifies then, of course, to 3xy squared, z to the 4th, and we're evaluating this where z goes from 0 to 2. So the 0 is just going to like knock out this entire expression, so really the only interesting thing that happens is when we plug in a 2, and that becomes, let's see, 2 to the 4th, so 16. 16 times 3 is 48. So this becomes 48xy squared. And we'll move on to our second integral, which is going to go from 0 to 3. I'm not writing out this entire thing. I'm just writing out the second piece. So integral from 0 to 3, 48xy squared with respect to y. So when we integrate with respect to y, 48x is a constant, and then this is y cubed over 3. The 48 and the 3 simplify. 48 divided by 3 is what, 16? So 16x y cubed, and then y is going from 0 to 3. Again, 0 is going to knock out the entire expression. 3 to the 3rd is 27, and I don't have a calculator here. 16 times 27, I'm just going to call it that maybe since I don't have a calculator, right? No, I guess it's 432. Okay, so this is 432, and x is still waiting to be integrated. So our last integral of our triple integral goes from, whoops, not that, goes from -1 to +2, and this is all in terms of x. And when you evaluate this thing and plug in the limits, if you want to pause the video right now, you can do that. When you plug in the limits, everything comes out to 648 on this one. 648, some sort of 4-dimensional units there. They're not units of volume, it's 1 dimension up from volume. Now, this first example was particularly friendly because the solid over which we were integrating is this box, so you have these nicely defined limits for x, for y, and for z. That's really nice. You can switch up the order here as long as you're consistent with your integration as well. This is like the friendliest triple integral that you can encounter, which brings us to a not so friendly integral for our second example. Now, Your last of the homework problems is sort of modeled after this example, and if you struggle with it, don't worry about that too much. I think this is a very challenging problem. So, the problem says, evaluate this triple integral. Notice the integrand z is actually quite simple, because the real challenge here is not the actual integration, it's setting up the integration and knowing what order is the correct order. So, no, cancel. So then it says, our solid over which we're integrating is the wedge in the first octant. Now, in a regular two-dimensional graph, these are quadrants. In a three-dimensional graph, each of the little sections is called an octant, and there are 8 of them. So in the very first octant, cut from the cylindrical solid y squared plus z squared is less than or equal to 1, and the planes y equals x and x equals 0. Now, I'm going to make some changes to this picture because I want to draw this solid before we start integrating at all, but I want to change the variables here. So instead of saying x and y, I want to make this one y and this guy z. I want to look at the yz plane just for a second. And the reason I'm looking at the yz plane is because most of the interesting part of the problem happens in the yz plane with this cylindrical solid y squared plus z squared is less than or equal to 1. It's a circle in this two-dimensional picture here, and then it would extend sort of out of the paper in the x direction, which I'll draw in just a second. But for right now, that is a circle. Now I'm changing my scale here significantly, so I'm making 4 of these little steps count as 1. So this is 1 up here, this is -1 down here, -1 and +1. But this is a circle. That's the circle y squared plus z squared equals 1, just in the two-dimensional yz plane. Now, one of the examples that we saw in the second section also had a cylindrical section, and one of the things that we did, was rewrite the equation for the circle where it was solved for one variable. And I'm going to do the same thing here. So instead of saying y squared plus z squared equals 1, I'm going to first say z squared equals 1 minus y squared, and then I can actually write z equals plus or minus the square root of 1 minus y squared. But there's actually sort of something interesting happening here. It also says in the first octant. So really, on that entire circle, this is the only portion that I care about. So I know I have this plus or minus here, but since I only care about the upper portion anyway, I really only care about the plus. So I can really just say z is equal to the square root of 1 minus y squared, and that's that red portion. So now I've got z solved in terms of y. So z has got these sort of curvy limits, which kind of suggests at the very least we won't be integrating with respect to z last, because we always do our nice numerical limits last. So the problem here is that this isn't really the whole picture, right? We're actually in 3 dimensions looking at this. So there's this x-axis which comes out this way. Now if you want to stop for a second and check that the right-hand rule works with the way that I've drawn these coordinates, you can do that. Your pointer finger will be here in the direction of the x, so your pointer finger is sort of like facing toward you, which makes your middle finger point to the right, and it makes your thumb point up. So this works with the right-hand rule as well. X, Y, Z, this sort of orientation is correct. And we're actually, I drew a circle, but it says we're talking about the cylindrical solid. So this circle extends sort of out of the paper. It's like it continues. I'm going to draw it in red again. It sort of continues back this way in the same direction as the x-axis, and over here as well, although remember I only care about the first octant, so I really only care about like this portion of the cylinder that's sort of like growing out of the paper toward you. So that's what's really happening. Now it also says this is cut by the planes y equals x. Well, the xy plane is sort of here, like growing out of your paper toward you, but in this sort of flat like defined by this axis and then this axis. So the line y equals x, or the plane y equals x, is sort of like extending out this way, which cuts this cylinder in sort of a strange way. I mean, it cuts it kind of like that. So we have this sort of slice of a cylinder that starts here on the y-axis, because x equals 0 is where it starts. So it starts here at x equals 0, ends here at this diagonal line, and it's really a cylinder this entire time. It's like a strange slice of like rounded pie or something. Like if you had a circular cake and you cut a slice from just the very top half of it, that's what your slice would look like. If you're having trouble visualizing this, or if you're not sure if you can do this on your own, that's fine. I think this is a challenge, and as you go through these examples and you practice in a class, this will start becoming more intuitively obvious, but don't worry if this is challenging right now. So now that we have this slice, one thing that I notice is that my x limits are also sort of not friendly numbers. Like x starts at 0, but it ends at this diagonal line. Z certainly doesn't have friendly limits because it ends on a curve. Really, the only one of these three variables that has friendly limits is in the y direction. So y starts here at y equals 0 and it ends here at y equals 1, which is important to observe because that helps me to set up my integral. Y is going to go from 0 to 1, and that is the very last integral that I'm going to take here. Y is the one that has friendly limits. And then aside from that, I sort of have some options with order, but I'm going to integrate with respect to x next. So x starts at 0 and ends at this diagonal line, y equals x, but I want everything in terms of, in the language of x, so it's going to be x equals y. It goes from x equals 0 to x equals y. That's with respect to x. And then the last variable that I need to integrate is with respect to z, and z goes from, z goes from 0 all the way up to, well, this curvy function, which we said was the square root of 1 minus y squared. 1 minus y squared. So here's our setup for our integral. We made sure that our nice numerical limits are last, and the integrand given in the problem is just z. So now I'm going to start this in order. Here's my first integral, integral with respect to z of z. So when I integrate z, I get z squared over 2. I'm going to evaluate that from 0 to the square root of 1 minus y squared. Well, 0 kills it all off, so really I'm only concerned about the top limit, and when I square the square root, it cancels the square root anyway, so I get 1 minus y squared all over 2. That's this entire first integral. Now I'm going to plug that into my second step, which is integrating from 0 to y. 1 minus y squared all over 2 with respect to x. Well, this is a little bit weird because there is no x in here. So this entire thing is just a constant. So my answer is going to be x times, well, really all of that, 1 minus y squared all over 2, and I'm evaluating x from 0 to y. Well, the 0 kills it all off, so really I'm only concerned about plugging in y, which makes this whole thing y times 1 minus y squared all over 2. And I'm actually going to expand this out because I'm going to integrate a little bit more in a second. So I'm going to distribute here and say this is the same as y minus y cubed. I'm going to say it's all times 1/2 because then I'll pull that 1/2 out to the front. So my last integral goes from 0 to 1, all in terms of y. This is 1/2 y minus y cubed dy. So I'm going to pull the 1/2 to the front because it's a constant. It really is a constant, not just we're treating it like a constant, but this one really is. And then I have y minus y cubed. It's actually a really friendly integral in the end. So this integrates to y squared over 2 minus y to the 4th over 4, and we're evaluating from 0 to 1. Now the 0 kills it all off, so really I'm just going to plug in 1 into this entire thing, and this becomes 1/2 times 1/2 minus 1/4, which is 1/8 is my final answer. 1/8 is my unit of volume on that sort of slice of some sort of cylindrical portion. And 1/8 is going to be not a unit of volume, it's going to be some sort of 4-dimensional unit, which we can't really visualize, but that is what it represents. Now at this point, you've done everything up through exercise 8, which starts us at exercise 9. Now you'll notice exercise 9 has nice numerical limits, so it's really just practicing integrating with respect to 3 different variables. Problem 10 is a little bit more interesting because now we actually have variable expressions in our limits, but kind of the same thing, just practicing. Same with number 11. Number 12 is going to be the challenging problem here. Number 12 is very similar to the very last example that we just did. So again, solid in the first octant that's bounded by a parabolic cylinder. So think about what this would look like. Maybe something that you could do here is start by thinking about what your picture looks like in the xz plane. In the xz plane, and I'm choosing x and z just because this is a sort of interesting equation relating x and z, so maybe think about what your xz plane looks like, and then using a correct right-hand rule, draw in y and think about where y comes into this whole thing, and see if you can evaluate the integral. You have all the solutions with you, and if you have questions about it, you can ask me in this week's office hours.